Hello friends, welcome to this video on Gauss Divergence Theorem part 1. In this video, we will see about the statement of Gauss Divergence Theorem and then we will try to apply it to a problem and see how we can verify Gauss Divergence Theorem for the given surface. Let's move on into the statement. Gauss Divergence Theorem states that if S is going to be a closed surface which is going to enclose a region of space with volume V, and if you have a vector called as F defined over here in your S which has continuous first order partial derivatives in B, then we say that by Gauss divergence theorem double integral over S F vector dot ds vector equal to triple integral over V divergence of F into dV. So this is going to be the base theorem. Now this base theorem can be simplified over here by taking that my ds vector can be written as n cap into the surface integral ds. So the ds over here has now been replaced as n cap ds. The second thing which can be done over here is going to be divergence of f vector. What is going to be divergence of f vector? We know that divergence is calculated by the dot product of the del and the f vector. So we replace this divergence of f vector over here by del dot f. So this is going to be the two changes which we are going to make sure that the simplification of the process becomes easy for us. So what is actually the Gauss divergence theorem doing is it helps us to connect a surface integral with that of a volume integral. So what we see on the left hand side is going to be your surface integral, double integral over S. And what we see on the right hand side is going to be triple integral over V. So double integral over S represents the surface integral. And what happens to the right hand side? We have triple integral over V which represents volume integral. So what does this Gauss divergence theorem brings out? It brings out a relationship that connects a surface integral with that of the volume integral. So if we are now ready with this statement, then we can apply it to a problem and see what happens. Let the problem statement be like verify Gauss divergence theorem for f vector is x square I plus y square j plus z square k, where S is going to be the surface of the cuboid that is formed by the planes x equal to 0, x equal to a, y equal to 0, y equal to b, z equal to 0 and z equal to c. We need to keep in mind the basic difference between a Gauss divergence and the Stokes theorem is that Gauss divergence theorem encloses a volume in which says we need to make sure that it has a closed surface. If only it is going to be closed on all sides, then it can enclose a volume. If it is open to one side or one or more sides, you cannot enclose a volume in it. So this is the basic difference between a Gauss divergence and a Stokes theorem. In a Stokes theorem, you will have one side to be open, so that you will have a curve C which is going to be the boundary of it. But in Gauss divergence, you have it to be a closed surface. Therefore, the closed surface, inside the surface, we will have the volume V to be contained in it. Therefore, what we are going to have is all the 6 phases of a cuboid. So, x equal to 0, x equal to a 2, y equal to 0 to y equal to b 3 and 4, z equal to 0, z equal to c is 5 and 6. So, we have totally 6 surfaces for the cuboid. The first mark for any question over here for verification will be given for the statement of the theorem. Therefore, state the Gauss divergence theorem. So, we know that by Gauss divergence theorem, double integral over S f dot n cap ds equal to triple integral over V del dot f into dv. So, what is going to be the surface on which we are going to integrate the quantities and get the values done? It is going to be referred as a cuboid. What is a cuboid? Cuboid is a 6-sided surface. So, when I am going to imagine in the 3-dimensional axis, what they have said is x equal to 0. Which is my x equal to 0? My ZOY plane will be called as x equal to 0. And now x equal to a. Which is my x equal to a? So from the origin, if I move a units over here, the quantity which I have will be x equal to a. And next, what we will have is y equal to 0. Which is y equal to 0? The XOZ plane, XOZ plane is called as, you don't have a y over here, so you call it as y equal to 0. If I am going to move, b units over here, in the y direction, then I will be getting y equal to b. Next, moving to the last one. What is it? X, O, Y. So what is going to be X, O, Y, which is missing over here? Z. So you call this as Z equal to 0 plane. And when you move C units in the top, what you will be getting is Z equal to C. So this is going to be the basic structure in which my integration is going to take place. So when it comes to a volume integration, what is going to be my right hand side? So let us begin with right hand side. You will have to keep in mind, whenever the word verification is given, you will have to compute a left hand side, you will have to compute a right hand side, and then for verification we need to show that both left hand side and right hand side are one and the same. So we will try to begin with the right hand side. What is there in the right hand side? Triple integral over b del dot f dv. So this volume of the cuboid has to be estimated. Now, can we fix the limits? So, where does our limit of x vary? My x varies between 0 to a. Where does my y vary? Y varies from 0 to b. Where does our z vary? Z varies from 0 to c. So, I have the three integrals over here on my right hand side, and the limits for the three integrals are now fixed as x varying from 0 to a, y varying from 0 to b, z varying from 0 to c. Okay, so come on, now we will evaluate what is there in the right hand side. What we want in the right hand side is del dot f. What is our del? Del is nothing but I dou by dou x plus j dou by dou y plus k dou by dou z. So this is going to be my del. What I am doing, I am taking dot product with f vector. What has been given as f vector for me in the question? X square I plus y square j plus z square k. So let me multiply dot product with x square I plus y square j plus z square k. So when I take the dot product, I need to keep in mind I dot I is equal to 1. J dot j equal to 1. K dot k equal to 1. All other mismatch combinations will make it as 0. Like I dot j is 0, j dot k is 0, k dot I is 0, and so on. All the mix match combinations will make it as 0. So what I need to do is just concentrate on my I component with this I component alone. So when I do I dot I, what is I dot I? This will become equal to 1. So what will I be left out with? Dou by dou x of the input over here is x square. Next, what will happen? I with my j. What is I dot j? 0. What is I with k? I dot k is 0. So the remaining two will vanish. Now let us move to the second component. J dot I. J dot I is 0. So what will happen to the next term? J dot j. What is j dot j? J dot j is 1. So what will I have is dou by dou y of your y square. So j dot k will be equal to 0. Now let us move to the third component. In a similar way, k dot I is 0, k dot j is 0. What you will be left out is just k dot k. So what is k dot k? 1. So what we will have is dou by dou z of z square. Now let us partially differentiate this quantity. X on differentiation gives us 2x, y on differentiation gives us 2y, and z on differentiation gives us 2z. So 2 can be taken outside as common. You will have x plus y plus z. So what is this quantity now? This is my required del dot f vector. What we are going to do with this del dot f vector? Now come on, go and notice the formula for your Gauss divergence theorem. What we have in the right hand side, we are evaluating right hand side, triple integral over b del dot f into dv. Okay, so it is triple integral over v del dot f into dv. Now what is this? This can be extended as del dot f. Just now we found it as 2 times of x plus y plus z. So how many variables are there? 3 variables. What are the limits for my variables? X varies from 0 to a, y varies from 0 to b, and z varies from 0 to c. So how I can write this dv over here as, I can write it as dx, dy, dz. So now it's time for integration. Take the 2 common outside. When I integrate with respect to x, y and z are constant. X on integration gives you x square by 2 and y plus z on integration gives you x. Now apply the limit between 0 to a, still dy and dz will be there, and 2 integrations of 0 to b where y varies and 0 to c where z varies will be left out. So I have 2 times of a square by 2 plus y plus z times of a. This is my upper limit, and what will happen to my lower limit? Lower limit will vanish. So 0 to c, 0 to b, this will be different integrated with respect to dy, dz. Now let us move to the second variable with respect to y. With respect to y, you have a square by 2 is a constant, so you will have 1y. Y times of a, so you will have a into y on integration y square by 2. Za is a constant, so Za y will be my quantity on integration. So apply the limit from 0 to b. Still we have what left out? 0 to c, dz to be left out. Okay, so now when I apply, this now gives me integral from 0 to c is there. Y takes the value upper limit and the lower limit. So it becomes a square by 2 times of b plus a by 2 times b square plus z a b. So dz is still there. Lower limit on integration applying 0 will be 0. So let me integrate this component with respect to z for the last time. So you will have 2 times integral from 0 to c. Let us retrace the quantity a square b by 2. A square b by 2. What is the second term? A b square by 2. A b square by 2. What is the third term? Z a b. Z a b. Now let me integrate all this with respect to z. So 2 times of, this is a constant with respect to z, a square b by 2 z. This is again a constant with respect to z. So I will have this again as z. AB is a constant, z on integration z square by 2. Apply the limit 0 to c. So 2 times of a square bc by 2 plus a b square c by 2 plus a b c square by 2. So what will happen now? This 2 in the denominator can be taken outside as common and can be cancelled off, which leaves you with a square bc, ab square c plus abc square. Now this can furthermore be simplified by taking a, b, c common from all the 3 terms, which leaves you with a plus b plus c in the brackets. So this is what I have evaluated for my right hand side of my Green's theorem. Now let us move on to the left hand side. What is going to be in the left hand side? You have the left hand side to be evaluated for 6 different surfaces. You have f dot n cap ds. So this is my left hand side. Now what we are going to do is, we have a cuboid. A cuboid has how many faces? It has 6 faces. So what we are going to do is, this S over here, I am going to split it as S1 surface 1, S2 surface 2, S3 surface 3, S4 surface 4, S5 surface 5 and S6 for surface 6. So this single integral is now split as 6 different integrals. And now this f dot n cap ds is computed for each and every component, and then if I am going to add it, it is my left hand side. So now what are the 6 surfaces over here for me? The 6 faces are the one which is going to be x equal to 0, x equal to a, y equal to 0, y equal to b, z equal to 0, z equal to c. So now let us try to visualize this data. So now this box has a front, a back, a left, a right, a top, a bottom. So the back, which is XOY, is called by the name x equal to 0 because in ZOY plane there is no x component. So the back is called as x equal to 0. When you move a units in front, you get the front part. So what is the name of the front part? You call it as x equal to a. What is the unit vector here? The unit outward drawn normal is I cap. It is in the direction of front. So what will be the unit vector for the back portion? So my n cap is going to be I vector. What is the n cap for my back vector? It moves in the opposite direction of I. So it becomes minus I vector. So now two phases S1, S2 is now over. Now let me move to the next two phases. What are they? A left, a right. X, O, Z plane. What do you call this X, O, Z plane as? Y equal to 0. Now you move B units over here and you will have this light blue plane. What is this plane called as? You call it as Y equal to B because it has moved B units over here. What is going to be the unit vector in the direction of y? It is your j vector. So my n cap will be equal to j vector. Now for the left value, your unit vector will be pointing in the opposite direction. So this will be minus j cap. So my n cap for my left portion or the left plane will be minus j cap. Now this is going to be my S3 and this is my S4. Totally 4 surfaces over. Now coming to the last two. What are the last two? A top and a bottom. Now coming to the bottom, x, o, y, which is missing over here, z equal to 0. So the bottom plane is called as z equal to 0. So what is going to be the, if I move c units to the top, then my top plane is called as z equal to c. So my top plane is called as z equal to c. What is the unit vector in the direction of z? It is going to be k cap. So my n vector is going to be equal to k cap. Now coming to my bottom plane, what will be the unit outward drawn normal in the bottom direction? My n cap will be equal to minus times of k cap. So now this completes my surface 5 and my surface 6. So totally I have 6 surfaces for which I have named the equations and I have also named the unit outward drawn normal. Now coming to surface integration. So when I have my XOY plane, the surface ds will be equal to, your x is missing. So what will happen? Your ds will be dy dz. So similarly, for your front also, what is happening? X equal to a. So your surface will be dy dz. You keep it in mind, whatever is the variable present over here, ignore it and write the remaining two variables. That will be the surface area. Okay, so for my left, what will be my surface? My surface will be equal to, my ds will be y equal to 0. So I will have dx, I will have dz. Again for here, what will be my surface? My surface will be dx and dz because y plane has to be cut off. So for my surface integration, I have dx, dz. Now for my top and the bottom, what is going to be the surface? I am cutting off the z plane. So I will have dx dy. So again for the bottom also, what is your surface? Dx dy. Now all the details which has been put over here in this diagram can be made in a very clear format of a table. So what we are doing is we are representing the 6 phases as S1, S2, S3, S4, S5, S6 and the front, back, right, left and top, bottom with their corresponding equations and the corresponding n cap vector, and then we have also noted out the ds vector. So x equal to a means leave x, write dy dz. X equal to 0, leave x, write dy dz. Y equal to a, leave y, write dx dz. Z equal to 0, leave your y, z, write dy dx. So all the quantities when you put in table, it will become very easy for us to evaluate. So now what is going to be my left hand side? My left hand side is nothing but double integral over s f dot n cap ds. So this double integral over s, what I am doing? I am integrating it into 6 different parts: S3, S4, S5 and S6. Okay. So now come on, let us put it over here. What is my F vector? My F vector is x square I vector plus y square j vector plus z square k vector. Why I need to write it? Because over here, the integration has to be carried out only with respect to f dot n cap ds. So I need to multiply this f vector with my n cap vector. So what happens in this case? I vector dot I vector will be equal to what? 1. So what will be I dot j and I dot k? It will become 0. So what will be the value of f dot n cap? It will be merely x square. So now what you do is, what is the value at the equation? What is the equation? X equal to a. So when I substitute x equal to a, what will happen to this quantity? You will have it as a square. So next, let me move to the back face. X equal to 0 minus I into I. What is I dot I? I dot I is 1. So now you have minus 1. So you will have this as minus x square. Okay. I dot j is 0. I dot k is 0. So the quantity is minus x square. Now what is the value at the equation? What I need to substitute is x equal to 0 over here. When I substitute x equal to 0, what you will have? You will have this as 0 quantity. Now moving on to the next one. Y equal to a is my equation. What is the unit vector? J. What is j dot I? 0. What is j dot j? 1. So what will be the quantity over here? You will have it as y square. What is j dot k? It is 0 again. Now substitute the value of the equation at this point. When y is equal to, now what will happen? I have a cuboid. So y equal to b and the next one will be z equal to c. So what happens at the point y equal to b? X equal to 0 to a in my the x direction, 0 to b in my y direction, 0 to c in my z direction. So now at y equal to b, what will happen? This will become b square. Now minus j. When I do minus j into j, you will have minus y square. But what happens to the value when I substitute it as 0? This will become 0. Next one, c. What is the unit vector? K. K dot I is 0, K dot j is 0. What is K dot k? K dot k is 1. So you will have this to be equal to positive z square. Now at the point z equal to c, this value will take the value c square. And minus k times of k, you will have minus z square. When I substitute z equal to 0, you will have the value as 0. So out of the total 6 surfaces, this surface has vanished, this surface has vanished, and this surface has vanished. So only S1, S3 and my S5 are going to be left out for my integration. So what happens over here? I can move on to say S2 is 0, S4 is 0, S6 is 0. What is my S1? S1 is nothing but a square into dy dz, dy dz plus what is going to be my S3? S3 is nothing but b square dx dz, b square dx dz. So this is my S3. And next comes my S phi. What is my S phi? C square dy dx. So it is C square dx dy. Okay, C square dx dy. Okay, so now we are ready to integrate this quantity. So this becomes double integral a square. What is the limit of y? Y varies from 0 to b. What is the limit of z? Z varies from 0 to c. Next, I can move on with b square dx dz. What is the limit of x? X varies from 0 to a. What is the limit of z? Z varies from 0 to c. Last, integral c square dx. What does your x vary from 0 to a? What does your y vary from 0 to b? So now if I evaluate these three integrals, then I am done with my left hand side. So come on, let us evaluate this three integrals. So my double integral a square, so dy dz, y varying from 0 to b, z varying from 0 to c. Double integral b square dx dz, x varying from 0 to a, z varying from 0 to c. Double integral c square dx dy, x varying from 0 to a, y varying from 0 to b. A square is a constant. Integral dy will give me y between 0 to b. Integral dz will give me z between 0 to c. Next term, b square is a constant. Integral dx will give me x between 0 to a, and integral dz will give me a z between 0 to c. Now the third term, integral dx is x between 0 to a, integral dy is y between 0 to b. Now apply the limit a square, b, lower limit is 0, lower limit is 0 for 0 z, and upper limit is c. Now this gives me b square a c, and the third term gives me c square a b. Now I can take a, b, c common outside. So I will be left out with a plus b plus c. So this is going to be my left hand side. So just compare, is the left hand side and the right hand side the same? So what did we have for the right hand side? My right hand side also is a, b, c into a plus b plus c. And what about my left hand side? My left hand side is also a, b, c into a plus b plus c. Therefore, we have verified the Gauss divergence theorem for the given f vector on the given cuboid. So this will complete. A quick recap, write the formula first, then move on to find out what is your del dot f here. Apply the triple integral limits over here and get your volume evaluated. That will complete the right hand side. Move on to your left hand side. Separate your single integral S as 6 different phases. Compute your table. This table is going to remain fixed when you know the 6 phases and their identical unit outward drawn normal. Just replace this f vector alone by the given question. Multiply this f vector with n cap and apply the equation's value over here. And then whichever is going to exist, that alone you integrate. So after integration, your answer will be compared with that of your right hand side and left hand side. If it is same, you verify Gauss divergence theorem. That's it. Have fun. Thank you.